So today we're going to be looking at common drain amplifiers, or source followers as they're called. Before we start off with that, common drain amplifiers, let's look at one very important concept of common source amplifiers. Let's review that and then we come back to this. So common source first. So by now I'm sure everybody knows this. RD, VDD, and AV in here. So to get, we got this, right? I mean, the gain is GM times RD, right? So to get a high gain, we always look at increasing the drain resistance to the maximum possible. But what if this stage was supposed to drive a, small resistance, right? If RD were to be lowered, what would happen? We lose a lot of signal level, right? What is AV, first of all? It's just V out over V in, as simple as that, right? So if you reduce RD, you're going to reduce gain, thereby you're going to reduce your signal level that's coming at the output, right? So we don't want to do that. We never want to lose gain, but at the same time we want to be able to drive smaller loads, right? So for this, to drive smaller loads, we use the common drain stage. Now the common drain stage looks like this. VDD. It's just as if you've inverted the common source stage. Excuse me. I have a little cold today, so I'm suffering from cold for the past few days, so I'm sorry about my voice or if I sneeze in between. Right? So this is V in, this is V out, and this resistance is connected to the source. And this resistance can be low, right? Now, this is called a source follower. It's also called a voltage buffer. We'll see why in some time. Voltage buffer or buffer stage. Now how this works is pretty simple. First, at the very input, we use this, right? Let me grab a nice color. We use this at the very input. And we give it a good input voltage and we get a fantastic gain here. And then this V out is V in now, right? We just connect these two nodes, these two terminals rather, and we get another V out from here. So the excellent gain we got from the first stage is buffered in this stage. I mean, it buffered in the sense it doesn't lose in its gain, and then we're able to drive a small resistor. What does basically driving a load mean? It's nothing big, you know. When you switch on a light, when you put a switch on in your room, it powers the light bulb. Now it drives the light bulb. What does that mean? It just lets some current pass through the resistance and the filament of the light bulb. So if you drive a current through a resistance, you're driving it. You're driving a load. Alright? That's all it is. So we get the high gain from the first stage and we put it in this stage, and then we let a small current pass through this stage to drive this load. This load can be anything in the world. It could be another stage as well, right? Excuse me. So that's all it is. Now we'll derive the gain of this stage and see why it's called a voltage buffer. Okay? I might make this video in two parts as well, so stay tuned. So if we take this stage and we start writing the equations that will lead us to the gain equation, we can forget about this part now. Alright. So V out is given by what? Before we do that, let's first plot V out, right? So for an example, to have something to start with. So we start increasing V in from 0. So this MOSFET doesn't turn on until it has reached VTH, right? So V out will be 0 until VTH. Let me grab a different color here. VTH and V out, and this is V out, and this is V in, right? So it is 0 until VTH is reached because it doesn't turn on, so it isolates this terminal here. So after it turns on, the V out follows the input voltage pretty nicely. That's why it's called a source follower, right? So that's all it is. When it starts to turn on, the MOSFET turns on. All that happens to V out is it follows the V in. That's why it's called a source follower, and it's attached to the source. So in this circuit, V out, all V out is the current that is driven into this resistance times the resistance, right? All right. And by now we all know that the equation of a current of current through MOSFET, right? So it's given by half mu n C aux times W over L VGS minus VTH squared times RS equals V out. Let me draw the circuit here again. So as we did with common source, I'll be drawing the circuit a lot of times so that it just gets imprinted in our minds, right? Helps me too. All right. Let's see here. VGS here is pretty simple, right? VG, the input voltage, minus VS, the output voltage, right? So that's all it is, right? It's pretty simple. It's pretty straightforward. Let's substitute that here and see what we get. Half mu n C aux W over L V in minus V out minus VTH the whole square times RS equals V out, right? Now we know that the gain AV is nothing but the partial derivative of V out over V in, right, with respect to V in. So it's just that, right? Just pretty simple. So let's differentiate this with respect to V in the entire equation. So what we get, all this is constant. So half mu n C aux W over L. Now this term becomes 2 times that term, right? So the differential of that. So 2 V in minus V out minus VTH times the differential of this. So with respect to V in, so this will become 1, right? So 1 minus del V out over del V in minus del VTH over del V in times RS equals del V out over del V in, right? Perfect. It's so long, but then we'll cut it short, don't worry. So first of all, 2 and 2 cancel. Then mu n C aux W over L VGS, this is effectively VGS, right? Minus VTH is what? GM, right? So GM, the entire term is gone, see? So 1 minus del V out over del V in minus. Now, let me put that in a box. Del VTH over del V in, right, is nothing but eta times del V out over del V in. I know I'm not being very legible here, but I hope you understand what I've just said. So that's 8 eta times del V out over del V in times RS equals del V out over del V in. Right? So instead of writing del V out over del V in, let me as well write AV, right? The gain, right? So GM RS, I'm just putting these two together. 1 minus AV minus eta times AV equals AV. Right? So if we can open this parentheses up, GM RS minus GM RS AV minus eta times GM RS AV equals AV, right? So we put all the AV terms together on that side, so it becomes GM RS equals AV and we can factor that out, right? Yeah. So we get here is GMRS plus. Oh, I forgot this. There's one more there. So GMRS plus 1 plus GMRS times eta, right? Now this is funny because I mean eta times GM is nothing but GMB, right? The transconductance due to the body effect, right? So let's do that now. AV. You know what? Hold on. Let's put AV on the left hand side so that things are more clear. AV equals GMRS over the entire thing goes down, right? 1 plus GMRS plus eta times GM is GMB. GMB RS, right? So we can just factor RS out of here. So GMRS over 1 plus RS times GM plus GMB, right? So that's the gain of this stage. Now pay attention to this gain now, right? Compared to the common source gain that we got. Oh, that reminds me, I should show you the common source output characteristics. Really interesting when you compare it with the common drain one. Excuse me. So this we got was GMRD, right? Now look at this here. It's GM times some impedance over 1 plus GM times some impedance, right? So if all these terms are really huge, you can forget the 1, right? And then RS can cancel. And then GM over GM plus GMB, right? So that is never more than 1, right? GMB is going to be something. It might be the lowest thing in the world, thanks to you eliminating your body effect. But then, what you will, you know what? I will review what I'm saying again. Don't worry. But then just suppose, right? If RS is really huge, RS is super huge, probably infinity. So what will you get? AV equals GM, because we can neglect 1 here because RS is already infinity. So RS over RS times GM plus GMB, right? So RS cancel. What you're left with is GM over GM plus GMB, right? Right? So even if you remove all the GMs from here, divide the whole thing by GM, what do you get? 1 plus 1? 1 over 1 plus eta, right? So just imagine your gain is never above 1. The best you can get to is just closest to 1 possible, right? For example, if you plot this as gain, or AV for that matter, what would you get? Just think about it. First you'll have no gain, and then you'll stop at this, right? 1 over 1 plus eta, and this is just 1.0. Sheesh, this is so not right the way I'm doing it. I mean, my handwriting, I'm saying. So (1.0), and this is 1 over 1 plus eta, right? So this is never over 1, right? So when you do this, right? This is just for illustration purposes. Don't go ahead and do this. I'm not really sure if we're allowed to do that already. V out, right? VDD, VDD, RD, RS, right? So this is like the initial input voltage, and then the output voltage of the common source stage is hooked up to the input voltage of the common drain stage, right? So this has a very high gain, but this has a gain less than 1. So but it's almost equal to 1. So it buffers whatever signal voltage comes from there, and is able to drive a small impedance without loss of the gain from this stage, right? So we might lose a bit, but that's not a big deal, right? So we'll of course talk about all that later. One more thing I wanted to tell you before we end here. Oops, I'm out of paper. Hold on. before we end here, is for common drain stage. We just in the beginning of the lecture we spoke about. I think this color is too bright. So common drain stage, we spoke about the output voltage against the input voltage, and we got something like this, right? It like doesn't increase till VTH, and then suddenly like follows the input voltage. Now look at the common source stage. If you remember, we've done that as well. Is V out over, against V in if we plot. Right? Even before I plot, you're already able to understand, right? Just imagine if this transistor is not on, if V in is increasing from 0, and the transistor is not on, V out is hooked up to VDD, right? That's it. So we're starting from here till VTH, and when we cross VTH, when V in crosses VTH, the transistor turns on, and there's a current driven through this impedance, right? So then your V out starts to fall, right? Remember this diagram from before? So just look at these two. It's a beautiful comparison, isn't it? So it's great to know. Good to have. All right, so I will continue in the next lecture on the small signal models and other things. Thanks for watching.